All right, let's take a look at this problem. Can sodium hydroxide be a suitable reagent to protonate this following compound? So first thing we want to do when we ask a question like this is the big kind of like this is the big question at the end of the chapter on acids and bases. If you can do this, then you've got everything mastered. So let's take a look. Well, the first thing we're going to need to do is we're going to need to write the acid-base reaction down. Hydroxide reacting with the alkyne, removing the proton, making water and an alkanide ion. Okay, so what do I need to consider? I can consider the atom, whether there's any induction, resonance, and the orbital that the negative charge is attached to decide about the relative stability of the conjugate bases, which ultimately indicates which acid is stronger. If I look at the atom, and generally that's the most important thing, oxygen is more electronegative than carbon. And so what this tells me is that the reaction would favor the reactants. Because if oxygen is the more stable conjugate base, that means water is the stronger acid. So the alkanide ion would be the weak, or the alkyne would be the weaker acid. So again, that tells us that the reaction would be reactant favored. And if I take a look at the orbitals, because we are what is different is the orbitals, then the alkyne is got an sp orbital, and the hydrogen on the water has an sp3 orbital. And so that would tell me that the alkyne would be the stronger acid and the water would be the weaker acid. And so we would say, in that case, we would say the reaction favors the products. But generally the atom overwhelms, or is more important a consideration than the orbital, and that is borne out by the pKa's. pKa here is 25 for the alkyne and 15.7 for water. So we know that the atom suggestion was correct, right? And that the water is a stronger acid. And so the reaction does favor the side with the weaker acid. That's reactant. So the answer to the question is no, sodium hydroxide is not suitable. Now it does ask us to propose a compound that could deprotonate it. So how about something like amide? Sodium amide, in the operating species there would be NH2 ion. So let's take a look at that case. Now, in this case, we're dealing with nitrogen. And so what do we say? Nitrogen, and it's still more electronegative than carbon. And so we would still say, okay, look, this reaction is reactant favored, because we would say the nitrogen is better at holding the negative charge than the carbon. So far, so good. Orbital, we would say the same thing we did before about the orbital. We'd say the sp orbital is leads to a more acidic compound than the sp3 orbital. So we would say that the alkyne is more acidic than the ammonia. And so we would say, okay, this is going to be reactant favored. Again, we get into the same situation that we were before. Well, what's the right answer? If we go back when we say, okay, well, the atom was the right answer before, that was what we picked there. Let's go back to the pKa's and take a look. Well, we know that the pKa here is 25, but the pKa here is 38. So it turns out that ammonia is actually the weaker acid. And so the reaction favors the side with the weaker acid. So the reaction actually is product favored. And so here's one of those situations where, yeah, the atom is usually the deciding factor. But here's an example of where actually the orbital was the deciding factor. And so sometimes the pKa's are going to be the things that help you determine that. Okay, so here's a compound. Is OH going to be able to do it? No, but amide, NH2 ion, anion, NH2 anion would be a suitable reagent to deprotonate the alkyne.